first of all, I would like to thank the organizers for organizing this wonderful event and for inviting me. It's a great honor for me to speak here. And well, as many people already said, one of the main features of Vershik's mathematical activity was his very wide range of his mathematical interests and his passion to learn new things and to relate them to his some favorite topics, and which lasted till the very end. So the topic I've chosen to speak about today is an example of such a situation. It's the last our joint project, which concerns the theory of hyperplane arrangements, which was totally new to him and totally new to me. But fortunately, we had a third co-author who, on the contrary, is one of the leading experts in the field. So we were lucky with that, Sergei Yuzvinsky. And well, the theory of hyperplane arrangements is a theory on the intersection of combinatorics on the one hand and algebraic topology and algebraic geometry on the other hand. And it now has a lot of application, including applications in, I don't know, in conformal field theory, but please don't ask me about it because I'm really not an expert. I do not know any details. But what is a hyperplane arrangement? It's just a finite set of affine hyperplanes in a finite dimensional vector space. It is a combinatorial and geometric object. And when we have such an object, what do we know about him? What we want to know about it? First of all, yes, there are two obvious characteristics which we know from the very beginning: the dimension of the space and the number of hyperplanes. But then the main object which captures all the combinatorics of what is happening is the so-called intersection lattice of the hyperplane arrangement, which is the set of all non-empty intersections of hyperplanes ordered by reverse inclusion. Well, so this object really captures all the combinatorics, and not only combinatorics. We'll speak about it a little bit later. And it is known that it is a geometric lattice with a rank function equal to the codimension of a subspace. And of course, when you have a poset lattice, the main tool to work with it is the Möbius function and the characteristic polynomial, which is constructed in terms of this Möbius function. And this is the combinatorial side of the matter. And as to geometric side, the interesting object, geometrical object, is the so-called complement of the arrangement, which is that the complement of all the hyperplanes. And an interesting and important characteristic is the number of connected components of this complement space. And if we know the characteristic polynomial, we know this number of regions. And you see here that already characteristic polynomial is something constructed purely from the combinatorics of intersections, but it gives the answer to geometric question. And also there is a distinguished algebra suggested by Orlik and Solomon, and it is now called Orlik-Solomon algebra, which also constructed from the intersection lattice, that is, it also from purely combinatorial structure. And the thing people are interested in is the cohomology ring of this complement subspace. And it turns out that this cohomology ring is in fact isomorphic to the Orlik-Solomon algebra, and thus even these characteristics is completely determined by the combinatorics. So, well, an example, the simplest example is the so-called Boolean or coordinate arrangement, which consists simply of coordinate hyperplanes. And of course, the number of hyperplanes is n, the number of regions is 2 to the n, and it is easy to see that the intersection lattice in this case consists of all coordinate subspaces of all dimensions, and so it is isomorphic to the set of all subsets of a set of n elements ordered by inclusion. It's a simple situation. We know the Möbius function and we know the characteristic polynomial. That was the simplest example, but now I should say the most famous example of hyperplane arrangements is the braid arrangement. It consists of the hyperplanes which in coordinates xi is equal to xj. So there are n choose 2 hyperplanes in this case, and the complement space is the set of all points with distinct coordinates, and it is easy to see that there are n factorial of them because to each permutation from Sn corresponds the region, the connected components where the coordinates of points are ordered according to this permutation. And an easy theorem says that this intersection, the intersection lattice for the braid arrangement is isomorphic to the partition lattice. That is the set of all partitions of a set of n elements ordered by refinement. On the slide you see the Hasse diagram of the partition lattice with n equal to 4. And the characteristic polynomial also can be computed in this case. And why this braid arrangement is very famous? Because of a famous result of Arnold related to the geometry, the topology of this braid arrangement, because in his famous paper of, I think, 69, Arnold proved that the complement space of the braid arrangement is a KG1 space where G is the group of pure braids. And correspondingly, the cohomology ring in this case is isomorphic to the cohomology ring of the braid group, a pure braid group. Well, and this Arnold's result ignited a very active, very intense activity in this field. There are many generalizations of his results to more general situations. And it is also the starting point for our project, but we also generalize the braid arrangement, but in quite another direction, of course, related to representation theory of symmetric groups. One of the most favorite topics for Anatoly Moiseyevich. And in fact, there was at least one result about the braid arrangement and representation theory, namely the symmetric group acts in a natural way on the cohomologies of the complement space, and the corresponding representation is of dimension n factorial. And of course, when anyone sees a representation of the symmetric group of dimension n factorial, he thinks that it is most probably the regular representation, but no, the right answer is almost regular representation, but not exactly. It is twice the representation induced from the trivial representation of S2. And this is a result of Lehrer. But this is for complicated structure, for cohomologies. But let's turn to the very beginning, to the braid arrangement itself. What is it from the point of view of the representation theory? And of course, the answer is obvious. The hyperplane xi is equal to xj is the invariant set of the transposition ij in the natural representation of Sn in Cn. But the problem is, how can we generalize this to other representations of Sn, to say irreducible representations? But what is the right construction? How can we construct a hyperplane arrangement, a natural hyperplane arrangement, in an arbitrary reducible representation of Sn? And of course, the naive answer fails. The naive approach is to take the invariant sets of transposition, but because it's meaningless, because for a general representation these invariant sets are not hyperplanes, so we cannot do this. And so the original problem was to find a correct generalization, and this is what I will speak about. First of all, some notation. This notation is rather standard, but still the set of n elements, the set of Young diagrams with n cells, the set of partitions of the set of a set with n elements. And in this talk, when I say partition, I mean partition of a set, not of a number, but a set. Partition is of type mu if the block sizes of it form a diagram mu. This is a set of partitions of type mu. Here, just in case, an example of such a situation. And then P lambda is, of course, the reducible representation of Sn corresponding to the Young diagram lambda. This is the space of this representation. S of A is the group of permutations of on a set A. And if we have a partition with, we can construct the corresponding Young subgroup in Sn. And if alpha is of type mu, we say that this Young subgroup is of type mu. And some notation more. If we have a set of transpositions, a collection of transpositions in Sn, we can take the group generated by this transposition. It is clearly a Young subgroup, which we denote as T. Again, you see an example, and I think everything is clear from this example. And these are standard notation for invariant subspaces of permutation or of a subgroup. A very almost obvious lemma from representation theory that if we have a irreducible representation P lambda and consider and we have a Young subgroup in Sn of type mu, then the invariant subspace of this Young subgroup in the representation is equal to the corresponding Kostka number k lambda mu. And this is almost obvious from the definition of the Kostka numbers, just one line. Let us look at an example. Take lambda to be the so-called standard representation of the symmetric group corresponding to the Young diagram n-1,1, and let T consist of a single transposition so that the corresponding Young subgroup is isomorphic to S2. And then, according to the lemma, the dimension of the invariant subspace of this transposition, which is the same thing as the invariant subspace of the corresponding Young subgroup, is equal to some Kostka number, which is equal to n minus 2, which is exactly one dimension less than the dimension of the whole space. So this is a hyperplane. And an important observation that we should make here is the diagrams lambda and mu. In this case, lambda and mu are conjugate to each other. This is important. Well, and here is the key theorem, again from representation theory, which underlies the whole our construction. Namely, suppose we have a Young diagram lambda and consider the corresponding, walk in the corresponding irreducible representation of a sen, and we have a partition alpha of shape lambda prime, that is not of the shape lambda, but of the conjugate diagram. And we consider an arbitrary collection of transpositions in Sn which generate the corresponding Young subgroup S alpha, and consider the sum, of course it is not a direct sum, but the sum of the invariant subspaces of all these transpositions. Then the theorem claims that this subspace depends only on alpha and not on the collection of transposition we've chosen, and the codimension of this subspace is equal to 1. That is, it is a hyperplane, and it is exactly what we need. So our construction of a natural hyperplane arrangement in the space of an arbitrary irreducible representation of a sen, which Anatoly Moiseyevich suggested to call intrinsic hyperplane arrangement, looks as follows. Exactly what we did in the previous theorem. We consider for each alpha a partition of shape conjugate to lambda. We take an arbitrary collection of transpositions generating this, the corresponding Young subgroup, take the sum of the invariant subspaces of these of all these transpositions, and according to the previous theorem, it is a hyperplane, and the collection of all these hyperplanes for collection of all these hyperplanes for all alphas from Pn of lambda prime for all partitions of shape conjugate to lambda. This is our main hero, the intrinsic hyperplane arrangement. Well, let us look at an example. The same example which we started to consider some slides ago. The standard representation of the symmetric group, lambda is n minus 1, 1. The conjugate diagram is 2, 1 to the n minus 2. And it is easy to see that in this case we obtain the invariant subspaces of transpositions. So this is exactly the braid arrangement. But not exactly, because there is the braid arrangement is defined in the natural representation in Cn, which is the sum of two irreducible representations, the standard representation the standard representation P minus 1, 1, and the trivial representation Pn, and this one-dimensional representation, the one-dimensional space, belongs to all hyperplanes, but it's it is not important because in terms of the theory of hyperplane arrangement, this means that the braid arrangement is the product of this intrinsic arrangement and the empty one arrangement, but essentially we just factor this one-dimensional subspace out and forget about it, and this doesn't matter. So we see that our construction is indeed a generalization of the braid arrangement. What can we say about these arrangements? Well, first of all, we can compute the number of hyperplanes, which is just the number of partitions of shape conjugate to lambda, and it is known, it is given by this number. But the main feature of our arrangements is that everything in them is SN invariant. Literally everything, whatever you take and want to look at, will be SN invariant, and it may feature, and we believe that it can be useful, and there should exist a theory of such arrangements. For instance, if we consider the unit normals to all our hyperplanes, they form an SN orbit for a natural action of SN on the set of partitions of a given shape. Of course, normals are defined up to a constant, but these constants can be chosen in such a way that this holds. And we may consider the convex hull of all these normals, and then we obtain a polytope which appeared in literature under the name of Specht polytope, and in the case of the standard representation, this is the root polytope of type A. And here is another example, a new example of a representation which we can compute everything. It's in a sense it's the conjugate case to the braid arrangement when lambda and mu change places. So lambda is now 2, 1 to the n minus 2, and lambda prime is n minus 1, 1. That is the Young subgroups we are dealing with are isomorphic to S minus 1, S n minus 1, and the dimension of the space is also n minus 1. The number of hyperplanes is n, and we can compute the characteristic polynomial of this arrangement. You see the answer on the slide, and you see that it is more complicated than in the case of the braid arrangement, namely it doesn't decompose into linear factors, which means in terms of hyperplane arrangements that the arrangement is not super solvable, but still here is an example. I'll skip this, and there is another construction of our arrangements, which in some cases is more useful, and it is interesting in itself. Well, let us consider the subgroup which is denoted here by W. This is the product of Reith products, and this is in fact nothing else than the stabilizer of a particular partition under the action of Sn on the set of partitions of given shape. And then we consider the corresponding induced representation, where the representation which we induce from is the product of Reith representations of this kind. So on the left factor we have the sign representation, and on the right factor we have the identity representation. And So it's a natural construction, and we can prove a lemma that says that the multiplicity of the irreducible representation P lambda in this large representation Xi is equal to 1. And everyone familiar with the representation, the classical representation theory of symmetric groups, sees that it is a generalization of the famous Frobenius-Young correspondence. So, and it is indeed the case for under some conditions, our lambda becomes exactly the Frobenius-Young correspondence, and well, and the theorem says the following: so we still want to construct the intrinsic hyperplane arrangement in the space of the reducible representation P lambda. Then we can proceed as follows. We take this large representation, this very large representation, and here is the space of this representation, and we consider the simplest possible coordinate arrangement in this big space. So in this big space, it's just the coordinate arrangement x, y is equal to 0, vanishes. But inside of this big representation sits our irreducible representation, P lambda, so we consider the subspace of this representation. And according to the lemma, this subspace is uniquely defined since the multiplicity is equal of P lambda in this big representation is equal to 1. And then we restrict all our coordinates, coordinate hyperplanes in the big space, we restrict to this small subspace. And what we obtain is exactly our intrinsic representation A lambda. So this is another construction, and it is especially useful and clear in the case of Hooke arrangements. That is, arrangement corresponding to Hooke representations, that is, representations corresponding to Young diagrams of the form n minus k 1 to the k, which are Hookes. So in this case, this big space U is just the exterior power of Cn k plus 1, which we, there are many realizations of this space. For instance, we regard it as this space of totally antisymmetric tensors. And then the coordinate arrangement is, of course, consists of the coordinate hyperplanes of the form written here. But it's not the end of the story, because we can simplify this picture using the well-known fact that the representation of Sn in such exterior power decomposes into two reducible representations, two Hooke representations with neighboring k and k plus 1 or minus 1, something like that. And if we use this decomposition and its structure, it's of course is also well known, we obtain the following theorem, which gives yet another construction of the intrinsic hyperplane arrangement in the case of Hooke representations. We consider the standard differential in the exterior algebra, as written here, and then we do the following. We take the kth exterior power of Cn, and consider the hyperplane arrangement in this exterior power, which is defined by this equation. The differential vanishes. Don't worry, at the next slide we'll see an example. And then the theorem claims that this is essentially the intrinsic hyperplane arrangement, but again up to a common subspace, which is the space of up to a common subspace of all hyperplanes, which we just factor out, and this additional common subspace is the space of the second. I've said that there are two irreducible components. With one, in one of them, we try to construct the hyperplane arrangement, and the space of the other, the other reducible representation, just gets factored out. Here is an example to make the whole construction clear. Let us take N5 and K2, so that we work with the Young diagram 3, 1, 1. And then our space is the exterior square of C5 of dimension 10, and the coordinate arrangements, I think it's an error, not coordinate arrangement, but the arrangements which the arrangement C, which we discussed here, is given by hyperplanes, consists of the hyperplanes defined by the equation of the form shown here. And these hyperplanes are indexed by triples of points, triples of numbers, distinct numbers I, G, K, from 1 to 5, and they have the following form: the differential vanishes. And all these hyperplanes have the common subspace, which is the space of the reducible representation with Young diagram 2, 1, 1, 1. And it has dimension 4. And if we factor it out, we obtain exactly our intrinsic arrangement of which has dimension 6. So this is the example how this construction works. And the next observation is, I will not speak about it further, but in order to construct the algebra, the Orlik-Solomon algebra I've mentioned at the very beginning of my talk, we should know the linear dependencies between hyperplanes, and it turns out that in this case these linear dependencies also in a sense have the form the differential vanishes. An exact statement is written on the slide, and an example in the case we are considering is this dependence between these equations, or the corresponding hyperplanes. And an interesting thing about these Hooke arrangements is that they are closely related to the so-called full simplicial matroids. There is a standard construction which, given a hyperplane arrangement, produces a matroid. The construction is very simple. The elements of the matroid are the hyperplanes, and a set of hyperplanes is said to be independent if the set of their normals is independent. So it's the most natural thing. This correspondence between arrangements and matroids is essentially one-to-one, not exactly, but for all practical purposes. And it turns out that under this correspondence, the Hooke arrangement, our Hooke arrangement, corresponds to the so-called full simplicial matroid, which is just the matroid of K faces in the N simplex. And when I discovered this fact, I was very happy. I thought, oh, it's fine now. Of course, people know everything about these full simplicial matroids. So now I'll read what they write, and I'll know everything about Hooke arrangements. But I was shocked when it turned out that, of course, the case of one faces, which corresponds to the case of the braid arrangement, is well studied, of course. But as to higher dimension, even starting from 2, nothing is known. And I found nothing in the literature, but then I consulted some experts, for instance, Gil Kalai, and he confirmed that, yes, nothing is known. So it was a little bit discouraging, because it means that the question is not easy. But on the other hand, it was encouraging, because it means that we are going in the right direction. So our construction produce objects that are interesting to people, that exist in other areas of mathematics. And what about the geometry of our arrangements? Also in the simplest case of the Hooke arrangement, we can prove that the geometry is also very different from the case of the braid arrangement, which I remind that for the braid arrangement, the complement space is a KP1 space, with P being the group of pure braids. And it turns out that for other hooks, for hooks with K greater than 1, this is not the case. The fundamental group of M is free abelian, and it can be deduced from this, with some additional considerations, that M is not KG1. So it has its geometry is more complicated. And also we obtain a corollary that the group generated by all reflections at all the hyperplanes in our arrangement is infinite. And this means that there is in the theory of hyperplane arrangements, there is a theory of so-called reflection arrangements, but they also have some symmetry, but this is not our case, because the reflection arrangements, they are by definition, the arrangements such as the group generated by all reflections are finite, and in our case it is infinite. So our class is new, and I'll skip that. And as to the further directions, of course, it is just the beginning, and there are a lot of questions, a lot of directions, and starting from maybe the simplest case of the Hooke arrangements to compute the characteristics of these arrangements, and to consider the representations in the cohomologies. And here again, all naive conjectures fail. So it's something not known. And the big question, up to the big question of developing a general theory of SN-variant hyperplane arrangement, which uses, in some meaningful way, uses the representation theory of symmetric groups. But we've started this project, and we have a paper published in Arnold Mathematical Journal, but then we tried to continue this project, and we discussed it with Anatoly Moiseyevich, I don't know, maybe a week before he died. And so, honestly, I still cannot force myself to continue this project, because it's emotionally it's difficult for me to return to these discussions and this topic. But I hope that in some time I will be able to do this. So that's all what I wanted to say. Thank you very much.
Any questions?
Yeah. There is always a question. Did you try to introduce to other finite reflection groups in their representations?
No, we still know very little about this case, yeah. So there is not time for yet another generalization.
Definition, generalized nature, to
of course.
So, what do you know about the intersection lattices of, even in the Hooke case? Like, can you describe them combinatorially?
In the Hooke case, yes, there is a simple description of the not of the lattice, but there is a simple description of the Orlik-Solomon algebra. But then we obtained some partial results, not yet published, in this direction, but they're partial. We still don't have any closed picture of this. So it's difficult, and the comparison with these full simplicial matroids shows that it is indeed, probably it is indeed difficult, but still we have hope.
I have a question concerning your last theorem about the fundamental group of the complement. So you said that for Hooke diagrams it will be virtually abelian.
Free abelian.
Yeah, virtually. Okay, free abelian. Yeah. And do you know if you would take? Do you know some other examples of other diagrams, not necessarily Hooke, where this would give some interesting group?
No. The case of arbitrary diagrams, not Hooke ones, is much more difficult. So at the moment we have no results about it.
No computation. Yeah. Mm-hmm.
Thank you for very nice talk. So, as far as I understand, characteristic polynomial is not computed in general. But can you compute at least the first steps, for example, for the computer?
Yes, this was the slide I've skipped. Here are computations for all arrangement with n equal to 5. And you see that indeed all, so we have a general formula for the last line in this table, but you see they look.
How far you can compute?
I'm not an expert in computing, so maybe I can do it for 6, but I think that no further. So my programming skills are not so good to cover large numbers, because for the symmetric group everything grows too quickly. So.
But they at least monotonic up to the middle, yes? As far as I understand, it's like no models. I mean, so it's growing up to the middle, or not up to the middle.
I'm not sure. some kind of course, some kind of this behavior, of course, takes place, but I'm not sure that it is exactly the case.
But each arrangement we can associate a graph matroid.
Yes.
And for hyperplane arrangement, it's full graph. And for this extreme hook with hyperplane, it's line graph. And what graph would be for arbitrary intermediate hook?
As I said, it's the matroid of k faces in n simplex. There is no better way to describe it. So you take a full simplex and consider all faces of the fixed dimension, and that what you obtain is exactly the hook case.
But it has to be underlying graph. Yeah, because if you graph to each edge, you correspond to hyperplane. To vertices 1, 2, 3, and EI. If you have edge joining I and J, EI minus AJ. If you have line graph, then it would be coordinates.
Okay, if there are no other questions, then let us thank Natasha. And,